everyone. So today we're going to be talking about the relationship between mass diffusive flux and molar diffusive flux. The situation is that there's a capillary tube with A on one side, it's a gas, it's a deal gas, and then B on the other side. You can take this away, and they're going to mix together. B will go over here to A, and A will come over here to replace it. So if we can begin by talking about molar flux, which would be N, and that will be equal to NA plus NB. And actually we can go further, and we can describe it in terms of concentration. So if you see, if you do NA, this would be molar flux. Molar flux. It'll be area. So it'll be concentration of A times area, and then distance. And that'll all be over T. Sorry, let's do flow. Molar flow. That'll be molar flow. And molar flux will be this molar flow. We do flow over the area. So we do concentration of A times the area times the distance over T, and that's all over A. So these will cross out, and you'll be left with concentration of A times distance over time. And this will be left with, obviously, velocity of A. Velocity of A. So, and that's flux, which is equal to N. And just like this, we can also do the mass flux. Flux, and I won't do the same thing, but it is the density of A times velocity of A. Okay. So, alright, so let's get started. So, this will be 0, and we can prove why. Since there's no space in between. So this is coming, one, mole will come over here, one other mole, they'll mix, right? So as soon as, say, one molecule leaves the space that it was in between, it's going to be replaced by it initially. So we know that NA is equal to negative NB. God, that's awful. NB, right? And because of that, we can just, put in NA minus NA is equal to 0. Right? And I'll show you why that's important. Let's get some more space. So the reason why that's important is because the actually, we can just write down the formulas for, this will be mass, write it down real quick. So this will be mass diffusive flux of A, of the component A, right here. And this will, that's that right? And then this will be molar diffusive flux of A. So we'll both do A. This will be the concentration of A times the velocity of A minus the average velocity of, average velocity. And then this will be density of A times the velocity of A minus, this is the mass average velocity. Okay, so like I showed earlier, we know that N is equal to the concentration times the velocity, right? And we can total, right? We know because they're both equally diffusing, we know that N is equal to 0 times concentration average. So we know that concentration isn't changing. It has to be some number. It is a number. So therefore, one of these has to be 0, right? You can't multiply together two things and not get 0. If it's equal to 0, that's not how this works. So the average velocity is going to be equal to 0, which helps out. We can now make this the molar diffusive flux is equal to the concentration of A times velocity of A. Right? So let's erase this, give it some more space. So the goal of this whole thing is to have a formulaic relationship between the mass diffusive flux and the molar diffusive flux. If you can do that, it's really important. Sometimes you won't want to use the molar diffusive flux, especially if if this is argon and this is hydrogen. Well, they're gonna have the same. Say that it's like 1 bar, and temperature is it's constant up, right? So they're gonna have the same moles, but they won't have the same mass. So that's why it will be very useful to have a relationship between the two. Okay. So since we have this, we can put it in terms of velocity of A. A is equal to the molar diffusive flux of component A over the concentration of A. And we can go ahead and put this VA right here. Cool. So we have this is the mass diffusive flux is equal to the density. Okay, so I cleaned it up a bit. It's kind of messy. So let's distribute out this. Be left with the mass diffusive flux over the density of A times the molar diffusive flux over the concentration of A minus the density of A times velocity. Okay, so we know that density of A over concentration is going to be equal to, let me just do it real quick. It's this is mass over volume. This is moles over volume. Volumes cross out, and you're left with mass per mole, which is the molar mass. It'll be the molar mass of A. So, let's say these two things will be gone, and we'll have the mass diffusive flux is equal to the molar diffusive flux times the molar mass of A minus the density of A times the velocity. Okay, so we pretty much have everything that we can reduce, but we can put velocity in terms of A and B. Okay, so we're looking at velocity now. So if we look at velocity, this is mass average velocity, so it's going to be over the total density, and it'll be density of A times the velocity of A and velocity of B. So these terms will be the mass average velocity. So we can take, say one of these terms. So we know that VB would be equal to JB over the concentration of B, right? So we can go ahead and put that into here. We can go density of A times the velocity of A plus, and we'll have this term. We'll have velocity of B over concentration of B times the molar diffusive flux of B all over the density, total density. So we already did this. We know that that's the molar mass. So we can kind of do the same thing with this term. So it'll be the molar mass of B, times JB, and that'll be plus this. So it'll be M, the molar mass of A times JA, which is the molar diffusive flux, all over rho. So we can also put this in terms of A, right? We know that JB is going to be equal to negative JA, right? That looks awful. Let me write that again. So we know that JB is going to be equal to negative JA because of the N that I explained earlier. So if we put that in, we're going to get MA minus MB, the molar mass of A minus the molar mass of B, times the molar diffusive flux all over the total density. Okay. So now this is equal to V, which we are going to put back into this formula. Okay, so now we're putting this back into the formula we derived before. It's going to be the mass diffusive rate, the mass diffusive flux of, and that's equal to the molar diffusive flux. I don't know how many times I'm going to say it, times the molar mass of A minus, and that's going to be the density of A times this whole thing. So I might have to make room. So it's MA minus MB, the molar mass of A minus the molar mass of B times the molar diffusive rate of A all over the density of the total density. Cool. Okay, so there's only really, I think, one more thing that we can do, and that's put this, this is over this. So you have the density of A over the total density. We know that this is going to be the mass of A over the, I can put it this way, mass total volume. Okay, sorry, I'm going to brain fart. So that's going to cancel out, and you're going to get the mass of A over the total mass. And that's going to be equal to the mass fraction, right? So that's going to be equal to omega A. So that's a mass fraction of A. So we can put that right here. So it's going to be, I don't know how many times to say it, mass diffusive flux, and then molar diffusive flux times the molar mass of A minus, so that's the mass fraction of A, times the molar mass of A minus molar mass of B, all multiplied by the molar diffusive flux. So let's put it in terms of, let's combine these. So we'll have JA, okay, and we're going to have MA, right here, minus the mass fraction that we just got there, times MA minus MB. And that is another one. All right, so there we go. So now we have the mass diffusive flux in terms of the molar diffusive flux and otherwise. So you can go back and forth. All right, I think that's it. Thank you very much.